How many of you watched a basketball game last night? Yeah. Okay, let's go ahead and get started. Welcome to the April meeting of the Alachua Astronomy Club. And as always, we do this in person and on Zoom, and we have a few folks on Zoom here. Okay. Page down. I'll try the third method. There we go. All right, and that's a neat picture. If you're new here, that was during one of the eclipses. James puts together a nice event for the public outside, and that was a great turnout for that one. Okay, tonight we'll do the standard stuff on the front end of the meeting, and then Dr. McAllister has come back. You know him. He's been here before. He's a club member and former director of Mount Wilson. He's got a 15-minute members corner on remote astrophotography. Then we'll take our break, and the break is outside, as you know, by the front door. And then we'll hear from Dr. Eric Perlman here, who's going to talk to us about active galactic nuclei. Okay, new members since our last meeting. Henry Bauer, are you here? How about Tim Dalrymple? How about, oh, I got a typo there, Richard Dasher. I'm sorry about that. Alex Kobitsas. Welcome. Glad you're here.
Yeah.
You showed up as a new member.
We need Donna and Blitzen.
Yeah. So Keith Lee. How about Wendy Mandel? Or Ellen Marafino? Or Joe Phillips? Okay, we've got 177 members now. Okay, just some of the things that's happened since we last saw you. Just a few nights after our last meeting, there was a total lunar eclipse, also known as a blood moon. And there's a graphic to show you what that was all about. And Dr. Cohen from his backyard got some really nice shots, and he created this composite image. Isn't that nice? Very colorful. Can you see coming in there? I want to make sure you don't fall over there. Okay. And then he labeled it so we could see which parts of the eclipse were what. Howard, what did you use? A camera?
It was a Teleview 76.
Okay.
Refractor.
Very nice. Very nice. Okay, we also had a star party at Rosemary Hill on March 21st, and that was a nice turnout. Beautiful weather for that. And Francisco gave us a tour inside the big telescope. And then the very next night, Matt put on an ATM at Chiefland, and he taught us how to make dew shields. And there's Dr. Cohen and Warren and myself there, and Matt making dew shields. And a little while later, Howard was busy again, and he took this picture at that star party with his 16-year-old camera, and it turned out beautiful. And then we've been busy. And then March 28th through the 30th was the spring picnic out at Chiefland. Really good turnout, really good food. You can almost smell the pork chops and brats and burgers, and had a swap meet as usual. Really good turnout. And that included the ribbon cutting for the Telescope Museum. It's actually called the Chiefland Astronomy Heritage Museum, as the sign says. And his Richard's there. He said a few words out front first, and then his daughter had the honor of cutting the ribbon. You can see on the left picture of her, she's got the biggest pair of scissors in Florida there. And then Richard had some really good words to say inside to everyone. And I hope, Richard, that you put that in one of the binders or a frame inside the museum. Those were great words. And as you can see, Richard has done a tremendous amount of work to put that museum together. Got some really great vintage telescopes, got a meteorite. There's Richard's old Zeiss down below on the left, and his old star chart from when he was a kid, I believe. And then a case full of vintage eyepieces. And then you remember Terry gave a presentation on Operation Moonwatch when Sputnik launched. There was no tracking system. So across the nation, they relied on young people like Terry to have a stopwatch and a telescope and to report. And they collectively got some very accurate tracking of that satellite. So Terry, did yours look something like that? Did your telescope look something like that one? Okay, that one's a Swift, but it was made specifically for that initiative back in 57, I guess. Okay, and then of course that swap meet and spring picnic included viewing every night. There's Matt with his new rig, and here's what he did, the Leo triplet. So isn't that beautiful? Okay, and then just a few nights ago, some of our club members supported open house at Rosemary Hill, and I'll just read what Dr. Latta just said. I wanted to express my sincerest thanks to everyone who volunteered at the open house at Rosemary Hill on Saturday night. It was a fantastic event. We hosted about 120 visitors who had a wonderful time observing Jupiter, the moon, several nebulae, in addition to learning about our telescopes and exciting science we were doing. Many visitors shared with me how much they enjoyed the evening and how welcome they were, knowledgeable, engaging, and professional our volunteers are, especially our students. A big thank you goes to our wonderful friends from the Alachua Astronomy Club, Lisa, Jerry, Frank, Ed, Larry, Karen, and Andy for supporting this event and sharing their time and telescopes with our guests. Their passion for outreach and for sharing the beauty of the night sky helped to make the night a very special one. So thank you very much. Okay, next Star Party at Chiefland is on the 19th. So put that on your calendar. That will show up on the website. It may be there already, I don't know. And then the next ATM that Matt's going to do, the topic will be how to select a telescope. So if you're thinking about buying your first telescope, that should be helpful. And also basic telescope maintenance, collimation of mirrors and cleaning of mirrors. And the last time we did that, cleaning of mirrors, Richard taught us how to clean mirrors, and there's Scott. He had bought a real nice used telescope, but the mirror was kind of dirty. And I'll let you decide if he did a good job.
Nice.
Look at that. Very, very nice. Okay, for the Far Out Journal Club, Dennis Coyce, who's the executive director at Yerkes, will be on with us on a Zoom on the 22nd of April at 7 p.m. And that should be really good because his background is very consistent with what the goal of the Journal Club is. And he's not an astronomer, he's a museum guy. So he's the perfect kind of guy to showcase that magnificent place there in Wisconsin. And then July 15th, we'll have Dava Sobel, the author of The Glass Universe. I'm about halfway through that audiobook, outstanding book. Don't want to miss that one either. Okay, a few words on equipment status. Bradley Miller donated 3 Celestron refractors, an 80 millimeter, 102, and that big guy at the bottom, 150 millimeters. That's a big telescope. No mounts, but they're all in working condition. And then they like Matt a lot. They keep sending him stuff. So 6 more SV 510 solar refractor telescopes were donated to the club. So now we've got 7, right? And we had a Russian-made Intez M606 Maxitov astrograph that we tried to sell at the club sale in January of last year, and nobody bought it. Ari just turned his back to it there. I mean, but it's probably because the case looks so nasty. This telescope itself was fine. So the club invested in a quart of paint and some high density foam to make a dedicated case for that scope, and we sold it for $425 on cloudy nights. I met the gentleman from Maryland who was passing through to head down to Big Cypress Swamp, and he was really excited about the telescope. There were 694 views of this on cloudy nights. So when you sell a telescope there, a lot of views is like 200, 300, maybe 400. 694. So there's a high interest in those kinds of telescopes. So who knows, if we get another one, maybe we ought to toss it in the museum. A lot of interest in that. Okay, round 2 of the facility repair took place, and there's Jerry and Tom. It's coming right along, looking good. So it was Warren there. Warren must have been the guy that took the picture. Thank you so much for that. And our final round of repair is this coming Saturday at 9 a.m. So just show up if you'd like to help out. Okay, I'd like to say thank you to Orlando. He has stepped forward to become the programs coordinator beginning in 2026. That's an important job. That's the person that gets the guest speakers. And we're fortunate because we live in an area that's rich in good speakers. So good luck to you. I'm sure you'll do great. We're going to have some outstanding presentations continuing. Yay. At this time, speaking of great speakers, let's hear from club member Hal McAllister, who's going to talk to you about his most recent remote astrophotography experience. Put that on your lapel there and just talk into that mic and that.
Whoops, oh, you're still hooked up.
Oops, I'm sorry. I've done that before. I'm sorry.
That's okay.
And then,
Thought I'd hook the big one.
and then to advance, you can either down arrow here
Okay,
or click on them.
okay.
Yeah, I've done that before.
Oh, yeah. I'm incompetent with tools like clipping things on my shirt. Here we go. Can you hear me? No. Yeah, now can you hear me?
Yep.
Okay, good. So it's a pleasure to be here tonight. Now, I was interested to hear about Project Moonwatch, which is how I got my start as a kid. I got hooked on astronomy. It was 1958, and I was in the 5th grade or something like that, or 4th, I forget, but a long time ago. And so I became a professional astronomer and worked at it for 40 years, retired a decade ago. I lived and worked in Atlanta, which has really cruddy skies, as you can imagine. We lived inside the perimeter for most of the time. And we came down, we moved to Gainesville because our daughter works at the university and we wanted to be near her. And we bought over on the west side of town, and I go outside at night and you could see the stars. And so I decided to go back to my roots as a kid and get a telescope. That's sort of my wife hasn't always approved of my purchases, but you know, I say you only live once, and we're getting older, and so why not? So she's very kind about that. So I got into modern amateur astronomy. I did astronomy as a career, but what amateurs can do just blew my mind today. And so I bought a few telescopes, and I've sold telescopes on astro.com and that kind of thing, astromart.com. And well, let me just get started. I'll show you how I got to where the subject of the talk is today. So how many of you have heard of Starfront observatories in Texas, where you can rent space, take your telescope out there and install it, and you can work every clear night. You can work yourself to death if you like. And I got enamored of this, but let me tell you a little bit about this enterprise first. This is really a brilliant concept. The guy who started it is a guy named Bray Falls, and he was 26 years old when he started it, just about 2 years ago. And it has buildings with roll-off roofs, and each one can hold dozens to 75 or 80 telescopes. And by the time I got there, they'd opened their 5th building, and my telescope ended up in building number 4. And you can see how the roof slides off, and there's this grand retinue of telescopes sitting there eagerly looking. Here they're looking at the North Celestial Pole, because that's where you have to park them. And you rent this based upon basically the floor space that your telescope projects onto the floor. So if you have a longer telescope and it has big swing arm radius, you pay more. The entry rate is $150 a month. And you can go up, if you have a big refractor or something like that, you can go up to a few $100s a month. And I, of course, opted for the smallest one. And it turns out that I made a mistake because I was too cheap to buy a proper cover to uncover they don't come by and take your lens cap off at night. So you can either let it get dusty or you can do something. And so I spent $19 on a linear actuator and built myself a thing that opened up. But when it opened up, it cost me another $50 a month because it exceeded that limit for my. Oh my God. So, but I fooled them now because there's a company called Deep Sky Dad, he's in Slovenia and he sells his products on in England. And I bought a cover that actually has a flat field system in it, so you can with a luminous panel. And instead of swinging out, it turns to the side, so it keeps the distance back. So once I get that out there and get it installed, I'm going to make them lower my rate again. Okay, so where is this place? It is in the heart of Texas. Its mailing address is a little burg called Rockwood, Texas. Population 80, I looked up tonight. And there it is marked there on this Google Earth plot. Has an elevation of 1,500 feet. And it's sort of starting to get in the arid parts of the Southwest. But it does rain there. And of course, the moon is still full there. So that affects your observing. The nearest town, I should say it's in Coleman County, Texas, that has a population of 7,000 people. So this is way out in the sticks. And here's a light pollution map of the area. And you can see DFW, Dallas-Fort Worth, and Houston. And it's surrounded by big Texas towns. The nearest town to it of any size is Brownwood. It's often associated with being in Brady, Texas, that has a population of about 5,000. You can see it's a little light island, but Starfront sits out on this dirt road in almost a treeless country, which is nice because of range fires that might be a problem. And it's in Bortle 1, 2. Now, where I live here, it's Bortle 6 or 7. In Atlanta, it was, I don't know, Bortle Infinity or something like that. So it's a very dark place. And here's my little rig. It's an ASCAR FRA. It's a PETSFAL 5-element objective with a 400 millimeter focal length. So it's f5.6 and it's got a 72 millimeter aperture. And I have sort of the standard retinue of ASI Air. I've really gotten hooked on ZWO products. So you may have followed their marketing, but they have a system and I've been a real sucker for them. They make great stuff, although it's in China and I guess they're going to go up here unless something happens. So you can see a filter wheel. There's an automatic focuser. I have purchased from them an image rotator so I can set the perspective up the way I like it. And that's also going to be installed when I install that Deep Sky Dad thing on the front. That will save me $50 a month and pay for the device in about 6 months. Oop, I'm pushing the wrong button. So here is I call it my Gainesville Observatory out of my driveway. And so that's the setup. I just roll it out. Of course, I have to align at the pole every night. And so you can ask the question, why leave? And I did a lot of work there. I really loved it. Well, the sky's bright. The weather kind of sucks from time to time compared to the Southwest. And the setup and takedown effort was becoming increasingly painful. Every night, you got to go out and align to the pole and so forth. And on top of that, and this is the real reason, I have very nice neighbors, but they're in love with lights.
Oh.
And this really is kind of a classic light trespass phenomenon because it illuminates my garage. It really lights it up. And also, if you look, you'll see there are shadows of trees on the driveway because there's a street light out in front of my house, which I didn't know. I remember as a kid going out shooting out a street light with a BB gun. I think the statute of limitations is exhausted on that one. But I'm not going to do that here, although it did burn out a few weeks ago and they haven't replaced it. This is not the ASCAR. I have a 5-inch telescope too that I'm sort of not using now. I may sell it. I don't know. But anyway, so that's the main reason. And here we were going to a family history event in San Antonio, and I decided to, because this was close to the Bray Falls is the founder, but it's close to Starfront Observatory. I decided to go ahead and take a plunge and spend the $150 a month. So we arrived. We drove down this long dirt road and there was a kind of a cattle fence and we went inside. Nobody was inside. It was about almost noon and nobody was there. And I thought, well, I told them I was coming and they said, fine. So I laid on the car horn for a while. Nothing happened. And off to the left of this is the quarters where the staff lives. They have these trailers that they live in. And I went to one and knocked on the door and pounded it. Nothing happened. I went to another one. And finally, after a while, Bray Falls himself, the founder, came to the door. And here he is with me out in front of one of the buildings. He's a really nice guy, very smart. And if you want to learn more about this, they produced probably 8 or 9 YouTube videos now about their venture. And here's the interior of one of their roll-off roofs. It's wall-to-wall telescopes. They have now about 250 telescopes. Subscribers who are paying, up to, the probably average person pays about $200 to $250 a month because people have big telescopes. They have night sky cameras, and these are just some screenshots I took a couple of days ago, early in the evening. You can see Orion in the picture on the left, and on the right, you can see Antares down there at the bottom, some Scorpios rising. This is a nice time of year for that. So the Milky Way is there. It is really dark, although I was never there at night, so I didn't personally get to see it. So here is an excerpt from a video where Bray Falls is walking through one of the buildings, and he just stops at mine.
Here is another system on an AM5. This one uses an ASI air for control. And the way you do that is basically you use our VPN
there a way I can turn it
to
up, or
run your whole system just off your phone app.
Well, anyway,
as you would if you
stop
were right
and he
next to it, and
talked
you can
about
do
this
it
little
remotely.
telescope.
So that makes things a little more simple.
ASI air there about on the side.
Again, a basic refractor,
But we'll just let
monochrome
this play
camera.
out. I encourage you to
Simple
watch
setup.
these. They're fun. It's quite an idea.
Yeah, we heard it on Zoom.
Okay.
We talked with, so we hear what I was saying, but we have to do something extra on our computer.
Okay. All right. No worries. Don't worry about it. We'll just continue on here.
That's all.
Well, that's no problem. We got back from our gathering back to here at Gainesville about a week after we dropped it off there, and this was last fall. And here is one of the first two objects I took. And this is it's in essentially white light. It's an RGB image with just UVA IR cutoff filter, and you can see the details of the equipment. It's these are 91 30-second exposures. I didn't want to overexpose the central core. I have problems with. I'm a newbie in PixInsight, and I'm steeply climbing that learning curve with much pain, but I'm getting there. Here's another one I took, and this is sort of what I wanted to emphasize I'm doing for fun. This is the North America Nebula in the center, and across the Atlantic from it is the Pelican Nebula sitting out to its side. And I decided that I would like to try to do mosaics. Now, when I started this, I didn't know that the ASI air is set up to do mosaics for you. So I reinvented the wheel and did it myself. It's a lot easier to do it in the ASI air. But I calculated offsets and allowed some overlap. And so that's the product. Here is each of these things is a 12 megapixel image, and there are 9 in that one. And this is zooming in on the Pelican. And you can see lots and lots of details. These are huge files, gigabyte sized files. I should say that the observatory has gigabit internet service, which is pretty remarkable for a county with 7,000 people to have that service. I don't know who they had to kill to do that, but anyway, they got it. So I decided to go for a bigger mosaic in Orion. And here's a star chart. And of course, everybody knows what Orion looks like, but I put it in blue outline anyway. And so this is where I stand right now. It's a 5x6 array in this mosaic. And I've decided that I've got to make it bigger to get at least the bottom stars, the Bellatrix and so forth in the field of view. But, and this is very much a work in progress, and I'm re-reducing all the data because dealing with things like Betelgeuse and Rigel and bright stars, Alda Lam and Alda Tech and Mintaka there in the belt is a real pain. Now, why didn't that go ahead? So here's the current mosaic. And the halos are gigantic around the bright stars, but these are among the brightest stars in the sky. But I've been learning about how to take care of that. So that will hopefully be better when I finally get through with this. But it is a work in progress. And zooming in, here's the core of the Orion Nebula. And I can point to my screen, but you can't see me pointing to my screen. But right in the center is the trapezium association, which is partially resolved. It's not fully resolved, but it gives you an idea of the kind of depth inside this. And that is a single image, and it is 22 gigabytes in size. So it's kind of hard to show that. And here is the horse head zoomed in there. And so it has a huge amount of dynamic range in this one image. You can barely see the horse head down there below to the right of the belt. So far, I've done 52 nights of data collection. I've gotten 9,000 files, almost a terabyte of data. I have my computer only has a 1 terabyte drive inside it. So I have an SSD on 4 terabyte drive. I store these things on. No significant problems except stupidity, making careless mistakes. Before Starfront, basically the routine was the setup and takedown of everything was time consuming, and I would make mistakes there too. And I stayed awake at night. In fact, I got up one morning, I was afraid it was gonna rain, and I was convinced it didn't rain. I got up one morning and my telescope was soaked. And it was because the stinking watering system in the yard came on, and it was my fault, you know. So at Starfront, you do the labor you put in is in programming the ASI air. It'll do everything for you. Just plan it and turn it loose, and it will put itself to bed so you get to sleep. So what's new? My PixInsight we've been running on my MacBook Pro was getting excruciatingly slow. So I just got, like 2 weeks ago, a Mac Studio computer with one of the M4 chips, and it's about 5 times faster. It's just scary fast. Although, of course, 6 months, Mac will have one that's faster than the one I just bought. And that's a big thing for me. And I told you that I'm installing this camera angle rotator and then Deep Sky Dad's observatory flat panel, which I will send out in a week or so and have them put it on. They'll work on your instrument for $50 an hour, or you can travel out there and do it yourself if you want to go to Texas. Knowing what I know now, would I do it again? You bet. It's great. Okay, that's it. Thank you very much.
So how many buildings were full of telescopes?
When I was there, they were just populating buildings 4 and 5. And now they have a total of 8 buildings. So, and it's a big piece of property. I don't know how many acres they own, but they can extend as long as people are subscribing to them.
Any other questions?
Yeah, how do you actually talk to the ASI air remotely? How does that, it's a Wi-Fi device, how does that work?
Well, you set up a VPN, a virtual private network, and you talk to it trivially easy. And it's made possible by the fact they have this gigabit internet service out there that's provided by the local telephone cooperative. But it works flawlessly.
Okay.
And you can download later data the next day relatively quickly. You can actually download right into the memory in the ASI Air. And I have an ASI Air that has more memory than the first generations. So it's great.
Thank you. One more in the back there.
Yes.
Does anyone rent out their telescopes over there?
That's a good question. There's nothing to prevent that, but I'm not aware of it. They have this huge user community with a vast Discord discussion. I'm not really into that, but you can log on. You don't even have to be you can join that Discord group even if you don't have a telescope there. And they're always yakking about this and that. Anything else? All righty. Thank you very much.
As a token of our appreciation, we'd like to give you one of these €2 Galileo coins uncirculated.
Oh, wow. Thank you.
You bet.
Yeah, lovely. Appreciate it.
You bet. Thanks again. Okay, does anyone have any announcements at this time? And if not, time for refreshments. You know where to go, right outside the front door. Please be back in 15 minutes and no goodies back inside the planetarium. And then we'll hear from Dr. Perlman. Thank you.
So I wanted to tell you about the meeting in June, because as one of the board members for the International Planetarium Society, we're having our board meeting that week in Chile. And then the week after that, I have my conference, the SEPA conference in Virginia.
Hang on just a second.
Yes. We need to put your stuff.
You need to put your, did you bring a flash drive?
So I have my, that's really cool.
Yeah.
Because I can,
A flash drive, I did not see slides on it.
shit.
Yeah, click those. That's okay.
Because I can show you how far this loaded. It's like the last few. Let me go to.
I mean,
view.
alternatively, I can just plug in my computer and we can do it that way.
Yeah,
Yeah, you would just connect to our Wi-Fi. And
so here's what it did. It went,
Okay, I can do that.
because what happened, it went to slide 60. Oh, wait a minute.
No, those,
Oh, yeah, you got it all.
you got it all.
Oh, good.
You got it all.
Excellent.
Okay.
Because earlier there were like 8
Because,
slides that
because
were
if I,
blank.
if I don't have to mess with that, then that's
Yeah.
great.
Those last 8 slides were just that background and nothing else, so.
Okay,
it
so
looks
good, good. All right.
So here's your microphone.
All right, which I'm gonna be putting way down here because I know how I
You
project.
speak, you project.
I'm a singer, so,
Okay, then you may not need this.
well, but I need it for people on the Zoom.
No, that's the one for Zoom. So, if you don't-
Oh,
yeah, so if you don't need one,
I will use the one for Zoom, but
How you
for,
doing?
in the room, there's no way that I need that.
okay. Sorry. All right, well, we will hold on to it just in case any of our more
Yes,
senior.
absolutely, absolutely, because I do want to be heard.
Yeah, yeah, but definitely the folks on Zoom will pick up from here, because this is working well.
Yeah,
Yeah, so you're at the Institute of Technology.
yes, I am. Yes, I am.
Yeah, looking forward to hearing your talk. So are you any relation to it's a Perlman?
Unfortunately not. I wish I had his musical talents. Well, I mean, you can certainly sing along with a violin, but, you know, not, yeah, I can't.
Back in and then pay for the,
Yep.
training.
Yeah, just Google Alachua Astronomy Club and it'll show up, and it's pretty
I think
self-explanatory.
we
There's
still
a
have
column of
business cards.
items on the left that says join, click on that, you can do it by credit card. So
Okay,
it's pretty painless, yeah.
By the way, Dave, are you, when he was talking, Hal was talking, I thought about something I hadn't thought about for several months. Are you aware of this?
Ooh, extreme deep field, no.
Okay, so this is something that a German amateur astronomer put together for Centaurus A, which is the very nearest radio galaxy. And it is just, it's insane.
Hang on just a second.
Doing as simple as that, just a.
How long, yep. How long ago were you a member here? How long were you?
Oh, gosh, it's been a while. Yeah, it's been a while. Because, I mean, I had to make some preparations for me to eventually set up, leaving town and leaving. So I was.
Okay,
Yeah.
so did you not know Dr. Cohen?
Um,
Because he's been a member a long time.
no, I
Okay,
didn't. I don't.
okay, all right. Well, it'll be good to have you. We have a lot of star parties, great bunch of folks.
That's fantastic. Yeah,
Good to have you.
thank you.
I'm sorry.
No, it's no
So
problem.
this is an amateur that did
This
this?
is an amateur that did this. It's insane. Okay, because you've seen pictures of Centaurus A, right?
Mhm.
And it's the elliptical galaxy that has that dust lane down the center.
Mhm.
This is 320 hours with his telescope. And I don't remember exactly what his telescope is, but I mean, just look at this. It is incredible.
Was he US or overseas? Or where?
He's German.
Okay,
He's German.
nice.
And I mean, the level of just detail in this, I mean, you can see shell after shell after shell of stars.
Mhm.
And you can see gas that's been shocked by the jet over here on
Wow.
this side. And the dust lane at incredible detail.
That's beautiful.
I mean,
Nice work.
so. It's an incredible mosaic.
So you're now in mute.
Yeah, I have a little bit. At least, one of them,
So I will first say a few words to introduce you.
Okay, I hope there isn't a problem with, you know, a closed water bottle.
Technically, yes, but no.
Okay. I just like to have a
Yeah.
little water available.
Yeah.
When I talk.
Understand. Okay, let's go ahead and get started. Okay, I'd like to introduce Dr. Perlman. He is an observational astrophysicist whose research concentrates on the nuclei of galaxies, their physics and evolution, particularly those in which the central black hole has a large rate of accretion and is abnormally active or active galactic nuclei. He also specializes in the structure and physics of high velocity outflows from compact objects and AGN, particularly jets. He has a strong interest in clusters of galaxies, galactic activity in clusters, and observational cosmology. And he was a member of the AGN science team for Canary Cam, a mid-IR camera spectrograph, the Gran Telescopio Canarias, and is now a science team member for the multi-object Miradas, the mid-resolution IR astronomical spectrograph in the Canary Islands. So I know, Terry, you've been to the Canary Islands, to that observatory. And that's a consortium that was led by UF, and now it's kind of a group leadership. Dr. Perlman came to Florida Tech in 2007 after his postdoc fellowships at Goddard Space Flight Center and the Space Telescope Science Institute, as well as research staff and research faculty positions at Johns Hopkins University and the University of Maryland. He maintains a large research group that includes typically 3 to 4 grad students and 15 undergrad research assistants. He also oversees the Physics Resource Center that helps students achieve greater success in physics and space science. In his spare time, he enjoys chess, singing, you can tell he's got a booming voice, Scrabble, reading photography, bicycling, and working out. Please welcome Dr. Perlman.
All right, well, that,
I need to get your sharing turned back on.
oh, okay, okay. Ah, yeah, I see what you mean.
Sorry.
Go right ahead. Go right ahead.
It's always something. Yeah, I love Zoom. I really do.
Yeah, well, I do as well. So, it's a necessary evil, isn't it?
Yeah, that's a good way to put it.
So,
Okay, I'm gonna try my best to get the Bluetooth synced up there because for some reason I don't see the Bluetooth thingy. 2 echoes in James' office. Okay,
okay. So,
you can go ahead and start.
well, that's a picture of me when I was considerably younger. Anyway, all right. So, I decided that what I would do today, rather than showing off primarily my work, is that I would bring you into the mind of somebody who works in the field and sort of basically show you how we as astrophysicists actually figure out what these objects are and, you know, what the size scales of objects are, particularly when we can't physically resolve them with a telescope. And the reason why this is important in active galactic nuclei is because many of the regions are too small to resolve with a telescope, whether we're talking about a telescope on the ground, in orbit, or even interferometric arrays. So I want to begin with this image, and it's an image that I suspect that most of you have seen many, many times, right? This is a part of the Hubble Ultra Deep Field. And I'm showing this to sort of give a little bit of ground truth to what it is that we are looking at. So we're looking at a huge number of galaxies at every distance. And I'm showing this to point out to you that a significant number of these galaxies have active nuclei. Okay, at any one time, about 1% of all galaxies have an active nucleus. Now, our nucleus, our galactic nucleus, excuse me, is currently not active. It's a good thing too, because if there is life on some of the planets that are relatively near the center of the galaxy, that life might not survive the nucleus being active. And the reason why is because there would be ultraviolet and X-ray radiation. There would also be a high velocity outflow coming from the nucleus, and that would probably destroy life on that planet. So I actually want to start out with our galaxy. This is, of course, the Milky Way. And this mosaic is probably also one that is familiar to many of you. This is the Milky Way at 10 different wavelengths. I'm very much a multi-wavelength astronomer. And so I don't just work in the optical, I also work in the X-rays, in the infrared, in the radio, pretty much every band. The center of the Milky Way. In these images, it's at the center. This is rotated so that the center of the galaxy is at the center and the galactic plane is horizontal in each of these images. And if you want to look at the center of our galaxy, you can't do so in the optical. And the reason you can't do that in the optical is because the center of our galaxy in the optical has a huge amount of dust, and the galactic center is obscured roughly by a factor of 100 billion. It is enormously obscured. You can see in the center that you are completely behind that dust lane. But if you go to the infrared, you can see what is there. Okay, so we're going to zoom in to the galactic center. The galactic center is at the position of that cross there. That is an optical image, and you can see not much is there in the optical, right? You can also see this image has pointed out lots of globular clusters and various other things. And yes, there's stars and gas, but it turns out there's quite a lot. So we are looking now in the top right at a mosaic zoomed in at various places at 21 centimeters. I particularly like the image at the bottom right, which is a mosaic of X-ray images taken with the Chandra X-ray telescope. And I put this up there to point out that there's actually quite a lot of exciting high energy events that are going on in the center of our galaxy. The arrow points to the position of Sagittarius A star. There is a lot of hot gas. All of those discrete sources are a variety of things. There's X-ray binaries, there's supernova remnants, there's a lobe of hot gas that came from a previous episode of activity. So yes, the black hole at the center of our galaxy has been active. Okay, the episode of activity that can be traced to is a couple million years old. Okay. This is a beautiful mosaic, two mosaics actually. The larger one is from the Meerkat radio array in South Africa. And it just shows an incredible array of radio emission surrounding the center of the galaxy. Sagittarius A star, the actual physical center where the black hole is pointed out by the arrow, but you can see just an amazing array of filaments and also gas clouds and a variety of other things. And then on the right, you can see a zoom up of one particular region taken with the James Webb telescope. I'm going to have some Webb images at various points in the presentation. Okay, so let's zoom in on the center of the galaxy. And then this is a near infrared image at 2 microns taken with the Keck telescope. The two arrows point out the position of the black hole. Lots and lots of stars here. But you're also looking at a small physical scale. So one of the things that you can do is that in the center of the galaxy, you can watch the stars move around. And you can watch them orbit the location of the black hole. Okay? So one of the cool things that, of course, we would love to do for other galaxies, but we can't because the resolution of our telescopes just isn't good enough, is that we would love to be able to look at the orbits of the stars. So you are looking at about 20 years worth of data in some of the images that you have there. And you can see that some of those stars approach quite close to the central black hole. And that unseen object, the black hole, has a mass of about 4 million times the mass of the sun. And this image, let's see if this plays. This is the 20 years of data that I promised you. Let's see if this plays. Hold on. There we go. So each of the points in here is an image with the Keck telescope. And as you might imagine, each one of the stars, each one of the stars gives its own set of constraints on what we know about the center. The tightest sets of constraints are given by the two stars that approach the closest to the center of the galaxy. And so one of them is this one which has its orbit in the yellow, which is called SO2. SO2 is particularly notable because in 2017 and 2018, it approached to within roughly 100 astronomical units of the black hole. So that is basically solar system sized, right? That is a little more than twice the size of Pluto's orbit. One of the things that was nice about that is because it's quite close to the black hole, we could do some interesting tests of both special and general relativity with that. I'm not going to talk about that, but those were quite nice. All right, so black holes. We actually do know that there is a black hole in the center of our galaxy. So a little bit about them. They are very massive. They are very dense. Their gravity has basically cut them off from the universe as a whole. They have a characteristic size called the Schwarzschild radius. If you were to make our sun a black hole in some way, please, let's not try that. It would be 3 kilometers in radius. And it would have an escape velocity that was greater than the speed of light. So no radiation, no information can get out. Now that we have observations with LIGO, we know that they exist definitively in stellar mass varieties. We also know that they exist in supermassive varieties. And the data that I just showed you from Keck was data that contributed to a Nobel Prize for Andrea Ghez of the UCLA Galactic Center Group. So black holes exist in most or all bright galaxies. So this is early work that was done with the Hubble Space Telescope. They looked at 35 other galaxies, and they found black holes in 33 of them. And they seem to obey a relationship between the mass of the black hole and both the luminosity and the velocity dispersion in the bulge. So the galaxy as a whole seems to know about that black hole. So AGN, we've known about them for 100 years. And I like to include a little history. This particular object is probably my favorite object, M87. Many of you know about it. Its jet was discovered in 1918 by Curtis Heber as a curious straight ray. And its radio emission was discovered in the 1950s. AGN also tend to have bright and often broad emission lines in their optical spectra. These are 7 different quasars, and then one of these objects, the second one is actually a sum of many different quasars, but you can see what their spectra look like. The bright, broad emission lines, particularly the hydrogen lines. These were one of the early things that people noticed. They also have bright optical nuclei. So 2 HST images are compared here. On the left is a Seyfert galaxy, an active galaxy. On the right is a normal spiral. And what I want you to notice is the unresolved nucleus in the center. Okay, and then here's another one of my favorite objects, 3C273. Its optical jet was also discovered in the 1960s. But what's notable about 3C273 is 2 things. First of all, its exact position was established by lunar occultation. And second of all, it was the first object that was discovered to have a high redshift. And that redshift, which showed a velocity of about 50,000 kilometers per second, implied by Hubble's law a distance of 700 plus megaparsecs, or about 2 billion light years away. And that was mind-blowing at that time. It's not so mind-blowing anymore. All right, so let's zoom in. But when I zoom in, I'm first going to give you what we think the model is, but then the whole point of this talk is I want to show you how we think as astrophysicists and how we test this. Okay, so you see the relativistic jets on either side. These are what I study. You also see the connection to the larger galaxy in the stars and gas and dust that stream into the center and eventually become accreted onto the black hole. When matter is accreted onto the black hole, what's happening is that as it streams inward, it is trading gravitational potential energy for kinetic energy. Okay, energy has to be conserved, but it can be transformed. And so kinetic energy shows up first as kinetic energy of motion, but then also thermal kinetic energy. So the disk of material gets hotter. It radiates. So you get luminosity, you get light. You also get an outflow. That outflow is important because otherwise you actually wouldn't get the material into the center, because to get the material into the center, you have to get rid of angular momentum. At the center is a supermassive black hole, and the regions immediately around the supermassive black hole are what give you the UV, the X-rays, and the gamma rays, and what launches the outflow that you see as the relativistic jets. Okay, so let's zoom in some more. And you can see the disk that we believe is in the very center of the whole engine. The black hole is there in the center. The disk sort of permeates the midplane. Matter is orbiting around the black hole in that disk. And it's very hot. Temperature is going up as it goes inward. And so that disk is radiating thermal radiation. And you can see that in the UV and the X-rays. Now, the green arrows track the material going inward. Notice that the disk at some point has to terminate. Interestingly, as we'll talk about in a moment, it doesn't go all the way in. And that's because relativity has something to say about it. Relativity sets a minimum orbit, a minimum orbital radius for a stable orbit. You can also see where X-rays and gamma rays come from. You can have material that is in the thin atmosphere around the accretion disk and around the black hole, which is much hotter than the disk. It can emit high energy radiation. And of course, we see some of that radiation directly, but some of that radiation also comes down, hits the disk, and then gets reflected back outward. And so you end up with a very complicated spectrum that looks like this. And I'm not going to try to explain it, but basically various parts emit different parts of the spectrum. Okay? So both active and normal galaxies have stars, gas, and dust. Virtually all galaxies have supermassive black holes at their center. Both of them, the center and the supermassive black hole is at the center of mass. And in spirals, it represents the center of their rotation. In elliptical galaxies, the matter is rotating around them, but we don't see the whole galaxy rotate. Okay? What is different is what the black hole is doing. In a normal galaxy, it's not doing much. Any matter falling into it is driven in just by the galaxy's rotation or by the random motion of stars and gas. And so there really isn't much light generated. We do see some, and I'm going to show you some of that in the center of our galaxy. But in an active galaxy, there is an active, much larger flow of radiation and matter, particularly matter, onto the black hole. The flow may be the result of a merger between two galaxies, and this is the process of accretion that causes the active galaxy. Okay? So that is what we believe is going on. We believe that AGN are caused by accretion onto a black hole. So we have this picture of AGN that includes a supermassive black hole, an accretion disk. It has locations for the high velocity clouds and the lower velocity clouds. It also has a dusty region, which we call the torus, in between them, so that we do see the broad line clouds in some objects, and we don't see them in other objects. Okay, so the question is, put yourself in my mind. How do we test this? How do we actually build this up and subject it to a variety of tests? Okay? All right, so this is why we need that torus. If you look at the objects on the left, you have type 1 objects and type 2 objects, and you notice that what's missing from the type 2 objects are these broad lines. And you also notice that the blue continuum is missing from those objects. The natural way to take care of that is by dust. We'll talk about that later. On the right, you see the spectral energy distributions that we see. Most objects share all of these characteristics that you see from the infrared all the way through the X-rays. The only difference between these two is the presence or absence of the radio emission. Okay, so I work mostly on jets. This mosaic is a mosaic I was involved in because this is M87. And M87 is an object I've done quite a lot on. The relativistic jets come out of the center of the galaxy, very close to the black hole, and they actually emerge at high speeds, up to 99% of the speed of light. And the way that they do that is by a coupling between the black hole, its accretion disk, and its magnetic field. The purple lines here are the magnetic field lines, and initially they start out straight, but what happens is that as you start the accretion disk rotating around the black hole, they get wound up, and the winding up of those black holes is what ejects material. All right, I'm going to skip to this. How do we test all of this? All of this is just a cool theory unless we have ways to test it. So we're going to start out with Sagittarius A star, which is our central black hole. We're going to look at what it does, and then we're going to move out to regions around it, use variability, what's called reverberation mapping. We'll use an assist from gravitational lensing, and look at some other regions deep inside the active galactic nucleus. So this is Sagittarius A star. And this is a series of images with the Keck Observatory. And what you're looking at here is that you are looking at short period flares that exist from the central black hole, timescales of several minutes, okay? The shortest time scale that's been observed is about 16 minutes. Why is that important? Okay, so who remembers what light travel time is from the Earth to the sun? 8. Yep, 8 minutes. Okay, so one Schwarzschild radius for Sagittarius A star is about 6/100ths of an AU. So this is placing that pretty darn close to the center. And in fact, this is material that's orbiting the center. This has to be hot gas within the last few stable orbits. And in fact, the mass density is so high that no other model works. This right-hand side is a plot of the constraints that you can get from the various regions, and the orbit of S2 only gets you to here. The X-ray emission region gets you to this region. There have been more recent observations with JWST that show that that's going on in the infrared as well. This is also what we see in quasars. So this is variability in quasars on timescales as fast as a few days. Now, many quasars have much more massive black holes. Much more massive black holes means that the black holes are physically larger. So they can't vary as fast. Oh, we already showed that. We're going to look at that continuum. Why are we going to look at that continuum? We're going to look at that continuum because that comes from the region right in the black hole's atmosphere, what we call its corona. And then we're going to look at the variability of this disk here. But as we do so, we're very close to the black hole. So we have to pay attention to relativity. The light rays are bent by strong gravity. Geometry is actually complicated. We don't know where the X-ray source is. So what we try to do is we use the data to figure out where it is, how big it is, and a variety of other things. So we get an assist from relativity in a variety of ways. So we're looking at a line in the X-rays, and that should be the Greek letter alpha. I guess that didn't make its way through the translation. That's what happens when you make your slides up on a Mac, and this is a PC. Mea culpa here. Okay. All right. So this is one particular object. This is MCG -6, -30, -15. And what you're looking at is its X-ray spectrum. And what they've done is that they have subtracted out two things. They've subtracted out the continuum, which is a set of power laws, two power laws. And then they've subtracted out absorption, both from our galaxy and its host galaxy. And so what you are looking at is the deviations from that. in this image at the top right. Okay. And then bottom right, they've taken out this soft X-ray excess. And so you're really looking here at the emission. And what you can see about the emission, and I apologize for the low resolution here, it's incredibly broad. Now, why is this broadness a problem? It's a problem because let's say you have material that is rotating around the black hole in a disk. Some of the disk's material is approaching us, and some of it is going away from us. And so what you would expect is this profile at the upper left. That is a disk that is purely Newtonian. Everything is orbiting in a Keplerian fashion. And so you would expect this kind of a double horned profile. Well, you don't see that, right? So let's keep going through what we need. Well, we know the material is moving fast. As you go close to the black hole, you start moving at a substantial fraction of the speed of light. And so you need special relativity. Special relativity does two things. It gives you a transverse Doppler shift, and you get a phenomenon called relativistic beaming. Relativistic beaming brightens artificially the material that is approaching you, and it dims artificially the material that is moving away from you. And so what you can see is that in addition to the line moving a little bit, which it has done, you also see the blue side get a lot brighter and the red side get fainter. Notice how this is beginning to approach what you see here, right? The blue side is brighter, the red side is fainter, but it's not enough. It's not enough because the light has its path bent by gravitational redshift. And so what this does is that it redshifts everything and it makes the red wing much broader. And then you get something that begins to look like what we've got. This is produced by material that goes all the way in to the innermost edge of where the disk is. And in fact, it goes so close in this object that it seems to require a spinning, rotating black hole. So black holes actually have their whole physics specified completely by their mass, their spin, and their charge, which we hope is zero. Yeah, really nobody knows what to do with a spinning black hole that is also charged. So I already told you about black holes. Black holes have an interesting property called the last stable orbit, or the innermost stable central orbit, or ISCO. At the ISCO, the orbital speed is c over the square root of 6, so 42% of the speed of light. Outside that point, matter can orbit indefinitely. Matter doesn't have to go in outside that point, unless it's given a push, right? But once matter gets to that point, the orbits are unstable and matter will spiral rapidly inward. So that is the inner edge of the gas disk. And there is also a minimum orbital period connected with that. And for a 10 to the 8th solar mass black hole, this is about 12 hours. Now, if you put the black hole and make it rotate, then the disk's inner edge can either move inward or outward, depending on whether the disk is spinning in the same direction as the black hole or it's spinning in the opposite direction as the black hole. So that particular object not only had its material at the very inner edge, emitting that iron K alpha line, but in addition, the disk had to be spinning in the same direction as the black hole. Now, some objects seem to be rotating in the same direction. Some objects seem to have the disk rotating in the opposite direction. How do we know the difference? We know the difference by how broad or how narrow that central line is. All right, I mentioned an assist from gravitational lensing. Gravitational lensing makes objects that are faint, that are behind a mass screen, appear brighter. This is an object where we can take advantage of it. This is the Einstein cross. It's an AGN behind a spiral galaxy. It has 4 images. And you can see those images in this optical image from a ground-based telescope. And on the right here, the grayscale image is what Chandra sees. And then somewhat rotated at the lower right, you can see an image of that with the JWST. And that's in the near infrared. Now, what you can do, each of those images is varying in a different fashion. Why is it varying in a different fashion? Because each image takes a slightly different path from the nucleus of the background quasar through the galaxy that's in the foreground that we see as the gravitational lens to us. And so what we can do is we can look at them, we can look at their variability. Each one also comes from a very slightly different region. The images should have their variability be correlated, but with a slightly different delay, which represents the path that they went through. So here's the idea we want to test. Let's say that the variability is caused by something that is close in, and then it propagates outward. We can use that, and we can use the variability that's found to actually test how large each region is. What we find is that the X-ray light has to be coming from within 10 Schwarzschild radius. What we find is that the optical light comes from further out at about 70 to 80 Schwarzschild radius. And here are those constraints. Here's the X-rays. And here are the radio. And how do we know the size scales from other regions? We use an assist from what we know from regular gravity. If we make the assumption that the material is orbiting the black hole, and we know how broad the line is for the emission lines, we can say, well, okay, that should be a prediction for how far out they are. And maybe I can use this same method that I just talked about. By the way, this method is called reverberation mapping. Okay, I'll tell you why it's called reverberation mapping in a second. So a line width of 10,000 kilometers a second, which is what we see in the broad lines, That's a 30th the speed of light. So that tells us, well, if we want to make a theory, it should come out at around 500 times the Schwarzschild radius, which for a 10 to the 8th solar mass black hole is around 5 to 6 light days. If we want to look at the narrow lines, they come out much further out. But that's actually something we can look at. We can actually observe it, resolve it. And the material in between has to be at intermediate radii. So why do we call it reverberation mapping? We call it reverberation mapping because we say, well, okay, we know that the region in the center is varying. And we basically say, well, okay, it's causing everything else to vary in concert. But the delay between the variations basically indicates how long the light from the inner regions has traveled to get to those outer regions. Okay, so UV or X-ray variability from the accretion disk is the prime mover. And then it propagates out to the broadline regions, propagates further out to the torus, propagates further out to the narrow line. You can also test one region of the disk against each other. Okay, for those of you who don't like calculus, ignore the integral. Okay, but seriously, I'm showing it so that you can see what we see as physicists. We have an echo that we're looking at it, and it's the combination of two things, what we call a convolution. And it's a convolution between the original event, which is the continuum variations, and whatever the response is. Okay? Now, on the left, you see what we want to observe. Okay? So we have an event that we can see in the continuum. Where's my pointer? And it causes this variation. Do we see that in the emission line? So here's H beta, a particular emission line. And notice that there is a delay between them, right? The same event is observed, but it happens a few days later. How do we pinpoint that? We do a cross correlation. So the cross correlation function is what you see over here on the right. Okay? Now there are obstacles to this. The obstacles include finite data length, sparse sampling, irregular sampling, noisy data, things like that. But this is what we do. This is what we do. And so this is 13 years of variability for one object. You can see optical continuum at the top. You can see broad H beta at the bottom. And I don't think it takes a PhD to observe that those two are highly correlated with each other. You see the same variability events, but one is very slightly delayed with respect to the other. And in fact, this was the data that I was showing you. This is one event here. The delay was about 7 days in this particular event. And the whole light curve, you could see the peak was around 6 days. You also get a relationship between the radius and the luminosity if you look at many different objects of different luminosities. Surprise, surprise, it comes out linear. This is about what we would expect. We can also compare high ionization lines to low ionization lines. We would expect that high ionization lines should come from a region that is closer to the black hole than the low ionization lines. Why? Because closer to the black hole, the material would be more highly ionized. And we see that. This is this ionization stratification. So this is various lines. Here's the continuum, H alpha, H beta, H gamma. And then these two helium lines are higher ionization energy. And you can see, so here are the two highest ionization energy lines, and they come out with a very low delay. And as you go to lower energy lines, they move out. But here's a surprise. Standard disk theory predicts a relationship between the temperature and the radius of the disk, such that the temperature goes as the radius to the minus 0.75 or minus 3/4 power. Well, we actually observe T going as R roughly to the -1 power. And we're not sure why that is. So not everything works exactly. I have my ideas about why that is, by the way, but it's not perfectly knit together. The infrared emission also seems to work. So this is the infrared emission. We can look at it as compared to the ultraviolet continuum. So this is one particular object, and you can see the two bands. One is the solid points, one is the open points. They're delayed by several hundred days. And so you get a rough size scale of light months. And this is about right. You know, you might have expected it a little further out or a little closer in, but when you do the numbers, it turns out that this is roughly corresponding to where you would expect dust to sublime, like carbon dioxide, dry ice does in the Earth's atmosphere. And in fact, with interferometry, we can actually image this dust. So this is imaging that was done in the mid-infrared. Some of the data comes from the VLT interferometer. And it turns out the size here from direct imaging for this central dust part here is consistent with what we see in reverberation mapping. The surprise is that we see some polar emission. We're not sure why that is either. So I'm giving you a glimpse into what I see, both how we test things and also the problems that exist. And so here's a summary of results from reverberation mapping. The broad line emission typically comes from light days out. Broader lines come from closer in. Narrower lines come from further out. Higher ionization lines come from closer in. And lower ionization lines come from further out. The X-ray and the infrared emission variability requires a black hole. The microlensing evidence requires optical emission further out than an X-ray, but we have some problems like this polar emission and like the radius temperature relation. So what is JWST seeing that's so neat? So what JWST is seeing that's so neat is that it's giving us a different view, a high resolution view into the central regions. I'm actually going to start out with an object. So this is actually not data from JWST, but this is from the LBT. But this is interferometry between the two telescopes. And the neat thing here is that in the optical, using interferometry, you can actually look at the outflow at this object. That's one of the neat things we're seeing. Here's JWST looking at the gas around a very red quasar. And what's neat is that when you look at this, you can see the motions of the gas. This is the gas that is accreting onto the black hole, as well as flowing out when you look at 90 degrees. It's also looking at the most distant galaxies. And this is where we get the biggest mystery. So the most distant galaxies, so let's go back to those deep fields, right? One of the big advantages that Webb has is that because it's not only a really big telescope, but also an infrared telescope, it's looking much further back in time, much further back towards the origin of the universe, the Big Bang. What it's seeing is that we have black holes that appear to exist very close to the time of the Big Bang, within only a few 100 million years of the Big Bang, as a matter of fact. So here you have a number of black holes that are seen in some of these deep fields, these squared objects. And these three are at ages between 570 and about 1 billion years after the Big Bang. And then there's this particular one, JADES GSZ 14-0, that is at this insanely large redshift. And that one appears to be only at about 390 million years after the Big Bang. The problem here is that we think we know how fast black holes should grow. And this black hole, just like the stars in the galaxy that host it, is too old. It seems to be too massive for that age of the galaxy. We don't know why. Now, one possibility is that it started out with a massive black hole before it started to grow. That is a possibility, but it is one of a couple possibilities. The other interesting thing that we're seeing, so this is the spectrum of one of those objects, is that this object is reionizing the space around it. Why is that interesting? It's interesting because the onset of the reionization of interstellar gas, this is an interesting epoch that cosmology talks about, and we can begin to use AGN at the earliest times to actually test this phase of what we know about cosmology. Now, another thing that Webb gives us is that it gives us an insanely high resolution view of active galaxies and also interacting galaxies. The nice thing about interacting galaxies are what we think spur a galaxy to become active. So let's project forward the Milky Way a few billion years into the future. A few billion years into the future, it will merge with Andromeda. It will produce a composite galaxy that probably during the merger might look like something like this. It might become very active at that point. Oh, And it also gives us a nice view into the variability of the center of our galaxy. This is data from 7 different days, as seen with the JWST at multiple different wavelengths. And you can see that the data is much better than what we looked at in the beginning part of this talk. And so this gives us much tighter constraints. So this is where I'm going to stop, and I'll take your questions. Thank you, everybody.
What is the different orbits of the stars? Why are they so different like that?
So remember that you have stars, distributed in some more or less random way in the center of the galaxy, right? And their orbits are oriented in random directions, and they're not all circular, right? They are highly elliptical, many of them. Many of them are highly inclined as respects to the plane of our galaxy. That's basically what you're looking at. If you were to zoom out and look at a great many of these orbits, they would appear to be orbiting in roughly random directions. And that one particular star that I zoomed in on, SO2, this just happens to be the one that we see orbiting the closest to the black hole.
Will they eventually be consumed?
So that's a great question. Possibly, yes. And in fact, it can't actually orbit too much closer because there is actually a minimum orbit that you can calculate before a star gets tidally disrupted. Okay, that happens to be at around 15 times the Schwarzschild radius. So it's not quite close enough to get there, but let's imagine that its orbit gets pushed a little bit, and that might happen. And then it could be tidally disrupted.
Someone in the chat said it's fascinating.
Well, thank you.
Okay, any other questions? Okay, if not, we would like to give you a token of our appreciation. It's
Thank
a
you.
mug with our logo and your name and the date.
Well, thank you.
You bet.
Thank you.
Okay, Paul pointed out to me that I had a mistake on one of the slides. The final repair date at NSP is on Sunday, not Saturday. So don't show up on Saturday wondering, where is everybody? So it's on Sunday.
Well, on Saturday, they'd just be blue shifted, right?
There you go. There you go. And also, Matt brought these in, and if any club member would like to check these out tonight, these automated telescopes, a dwarf, and is this a sea star? Yeah, you can do that, and you get magnificent results. So, yes. Okay, so we were going to have James Albury give a planetarium show next month, but he and I are going to coordinate. We're going to have some changes to the schedule, so just watch the website and you'll get the usual emails to tell you what the real schedule is going to be next month. And then also Members Corner, Matt is going to talk about the very small array. So, anything else from anybody? All right, thanks for coming. We'll see you next time.